with the regression problems we've been looking at lately, we were using mean squared error and root mean squared error as our primary generalization metrics. However, we don't use those when we use classification models, and there's actually many different generalization metrics that we can use for classification models. But the primary ones that you're going to see revolve around three things. One, the accuracy metric. Number two is what we call the confusion matrix, and there's actually many different bits of information we can pull out of a confusion matrix. And then building on top of the confusion matrix is a way to look at what we call area under the curve, or AUC. So let's take a look at these three. And to do so, we're going to actually use this model down here, which is a logistic regression model, where attrition is a function of all predictor variables in our data. All right, so accuracy is pretty much what you would expect it. It's how often is our classifier correct. So basically, when an employee either does leave the company or does not, how often do we actually accurately predict that? And so in this case, we see that our model is about 88% accurate. And to get this, we follow the same pattern that we did when we were doing the RMSE calculation, except we are actually going to pipe this information here into the accuracy metric. And again, we just pass it the actual attrition response variables and then the predicted or the estimated. And that allows us to compute the accuracy. Now the problem with accuracy is it doesn't tell us when we are actually mispredicting, like how are we mispredicting? And we can get that information by using what's called a confusion matrix. And this compares the actual categorical levels or events to the predicted ones, right? So you can see here on the left-hand side, we have our actual events and our actual non-events. And up here, we have our predicted events and predicted non-events, okay? So we are just simply going to have the number of events that we predicted were going to happen and that actually happened, the number of events that we predicted were not going to happen and that actually didn't, and then those where we predicted differently from the actual events, okay? Now, depending on how we mispredict, for example, if we were to predict that an event was not going to happen, however it did, right? Then we would have that observation in this upper right-hand box. If we were to make a prediction that the event was going to happen, but it didn't, be the lower left. And we can get those, we turn these into what we call false negatives and false positives. So a false positive is when we predict that something is going to happen, or in this case, in our example, if we were to predict an employee was going to leave the company and they did not, that's a false positive. A false negative is when we predict that the employee is not going to leave the company, but then they actually did. Now, we can get this confusion matrix for our predictions. And again, we follow the same pattern. We take our model, we make our predictions. We're going to add in the actual response variable. And then we use this conf_mat function, and that's going to produce our confusion matrix. So now you can see that we have predictions here. So when we predict no versus yes, and then truth is the actual, right? So if the response variable actually was no versus yes. And now we can kind of see where there are a lot of observations where the employees do not leave, right? We get 353 where we predict they don't leave and they actually do not leave. And then we have 34 cases where the employees did leave and we did predict that they were going to leave, right? So if we were to combine these two numbers and divide that by the total number of observations, that would be our accuracy metric we computed before. However, this allows us to see when, in fact, maybe we predicted that they were going to leave, but they did not. In that case, we have 17. So those were false positives, right? So we can see that we had 17, so that means we have 3.8% of our mispredictions were false positives. And then there's cases where we predicted they were not going to leave, but the employee in fact did, and that was 38. So those are false negatives. So we actually have 8.5%. So in this case, we can see that our model is actually being more conservative, meaning it's predicting no, they're not going to leave, when in fact they do leave. We miss that more often, right? And so this is quite informative. And we can actually make adjustments to our model if we wanted to try to balance this out. But just realize that we can get this idea of understanding, is our model predicting more false negatives versus false positives. And that kind of tells us how are we mispredicting with our model. Now, often we want a classifier that has high accuracy, but also does a good job of predicting events when they will and will not occur. And so this means we're trying to balance both false positives and false negatives along with the accuracy metric. And to get that, we can use this thing called area under the curve. Now, before we get to area under the curve, there is a plot that you see quite a bit when you do classification models, and it's called the receiver operator curve, or the ROC plot. And this plots the false positive rate along our x-axis and the true positive rate along the y-axis. Okay, and so if you had a straight line going from this lower left to the upper right, this would mean that basically our model is doing no better than just random guessing, right? Basically a 50% accuracy, and we balance true positives and false positives, right? And so what we want is a model that has our ROC curve where it goes higher to this upper left-hand corner, okay? And this means that we have high accuracy and that we're also balancing the true positive and false positive rates, okay? And so AUC, the area under the curve metric, is just computing what that area under this line would be, right? So a 1 is the highest we can get. And so if you have something, this line right here may be like a 0.83, this one may be a 0.75, this one a 0.6, and then again this dotted diagonal line would be a 0.5. So higher value indicates a better balance between overall accuracy and balanced mispredictions. So with R, we can go ahead and we can create our ROC curve. So here we take our model and we just simply, again, make the predictions, add in our actual attrition data, and then we do a ROC curve where we have the truth against the predicting no, and that provides our ROC curve. We just use this auto plot, which is going to automatically create this plot for us. And we can see we are doing much better than this dotted line, which is a good thing. But what is that? What is that AUC? Well, we can get that by using the ROC AUC. And so now we see that our ROC curve is actually 0.886, so right about 89%. That's our area under the curve.